The night sky seems like a still and silent painting, but that is a beautiful illusion. Look closer, and you will see the universe is alive with motion. Galaxies, those colossal islands of stars, are not isolated. They are partners in a slow, gravitational embrace, spinning, pulling, and sometimes crashing together in events of breathtaking scale. This is the dance of the galaxies. By the end of this journey, you will understand how these cosmic collisions built the universe we live in and even dictate our own galaxy's future. We will uncover how a single, invisible force orchestrates this ballet across billions of years and witness the stellar fireworks that erupt when galaxies entwine. What do you believe is the most beautiful outcome of chaos? This gravitational dance defines the cosmic landscape. To call them dancing galaxies is more than just poetry. It is a precise description of a slow, intimate, and transformative process. We often picture galaxies as lonely islands in a vast sea of darkness, each one a self-contained universe drifting in isolation, but this is a cosmic myth. The truth is far more connected and dramatic. Galaxies are social creatures, bound together in clusters and groups by the unbreakable threads of gravity. Over billions of years, these threads pull them closer, initiating a waltz that can last for eons. This dance is what astronomers call a gravitational interaction, or, in its final, spectacular act, a galactic merger. The forces at play here are immense but subtle. As two galaxies draw near, they do not simply crash head-on like billiard balls. Instead, gravity begins to stretch them. These are tidal forces, the same kind of pull our moon exerts on Earth's oceans, but operating on a scale so vast it can warp the shapes of entire galaxies, pulling out long, luminous streamers of gas and stars that look like celestial ribbons. This initial stretching is the first step in the dance. As the galaxies continue their orbit, drawn inexorably together, this interaction triggers something incredible within them. Vast clouds of gas and dust are compressed, igniting a frenzy of new star birth known as a starburst. Whole generations of stars can be born in these fiery nurseries, lighting up the galaxies with brilliant blue light. This is not a rare or catastrophic accident in the cosmos. It is a fundamental engine of change. Most of the large galaxies we see today, including our own Milky Way, were built through a history of these mergers, each collision adding stars, reshaping structures, and forging new celestial forms. The quiet, static universe is an illusion behind the scenes. It is a ballroom of titans spinning in a slow-motion ballet that builds everything we see. This invisible choreographer is gravity. It is the silent music to which every galaxy moves, a force so fundamental we can barely comprehend its patience. Gravity does not operate with the urgency we experience in our daily lives. It works on a timescale of cosmic eons, weaving its influence across distances so vast they numb the mind. Two galaxies separated by millions of light years are not isolated. They are connected by an unbreakable, elastic thread of attraction. Over billions of years, that thread slowly reels them in, initiating a gravitational dance that is less a collision and more a slow-motion tango. First, they begin to orbit one another, their mutual pull setting them into a spiral that can last for hundreds of millions of years. As they circle, they do not remain pristine. Gravity's pull is not uniform. The side of a galaxy closer to its partner feels a stronger tug than the far side. This difference, a tidal force, begins to stretch and distort them. Imagine two dancers spinning, their outstretched arms elongating toward each other, creating beautiful, streaming arcs of light. These are tidal tails, colossal bridges and streamers of stars and gas pulled from the galaxy's bodies, the first visible sign of their intimate entanglement. This dance has a predictable, though spectacular, finale, a merger. The galaxies, having lost orbital energy, draw closer and closer until their structures are utterly blended. Their central black holes may eventually spiral together, and their stars are thrown into new orbits, creating an entirely new galaxy. But there is an unseen partner in this ballet. The gravity we observe from the stars and gas alone is not enough to explain the motions we see. There is missing mass, a hidden influence that provides the extra gravitational glue holding galaxy clusters together and guiding these cosmic dances. We call this mysterious component dark matter. It forms vast, invisible halos around galaxies, and it is the gravitational framework of dark matter that often makes first contact, dictating the initial steps of the dance long before the luminous stars ever begin to feel the pull. So the choreography we witness is performed not just by the stars we see, but within an unseen arena shaped by the universe's deepest secret. A perfect example of this cosmic stretching is unfolding right now, over 290 million light-years away in the constellation Coma Berenices. There, two spiral galaxies known collectively as the Mice Galaxies are locked in a gravitational embrace so beautiful it has become an iconic portrait of creation and chaos. Officially catalogued as NGC 4676, they are named for the two immense, luminous tails of stars and gas that stream behind them, each stretching for over 200,000 light-years, resembling the long tails of a pair of celestial rodents. This is not a snapshot of destruction, but a portrait of the initial, graceful phase of a merger. The Hubble Space Telescope captured their intricate structure in stunning detail, revealing not just the tails, but the brilliant blue knots of newborn star clusters ignited by the collision, and the distorted, warped shapes of the galactic cores themselves, pulled like taffy by their mutual gravity. The mice are showing us the moment the dance becomes visible. They have already made their closest pass, like two dancers brushing past each other, and the gravitational tides from that encounter have done their work. Those spectacular tails are material literally pulled out from the bodies of the galaxies, a testament to gravity's power to sculpt on an unimaginable scale. This stage tells us that a merger is a prolonged and delicate process. The galaxies are not instantly blending, they are first being drawn out, reorganized, and stirred. Their individual identities are still clear, but they are now forever changed, connected by bridges of stolen material and caught in an orbit that will, over hundreds of millions of years, draw them back together for a final, unifying collision. The Mice Galaxies are a fossilized moment in time, a cosmic lesson showing us that even the most violent processes in the universe can have a phase of breathtaking beauty. While the mice show us the first dramatic stretch, other pairs reveal how the dance can create stunning order. The Whirlpool Galaxy, known as M51, is perhaps the most beautiful example of a gravitational duet in progress. Its perfect spiral arms, a classic example of what astronomers call a grand design spiral, sweep out from a brilliant core in an almost hypnotic pattern of cosmic dust and star clusters. But its perfection is no accident, it is the direct result of a celestial partner. A smaller, irregular galaxy called NGC 5195 is not a background object, it is the choreographer. In the past, this companion passed closely by the whirlpool, and its gravitational pull acted like a sculptor's hand, compressing the vast clouds of gas within the larger galaxy's disk. This compression triggered a chain reaction, igniting waves of intense star formation along the spiral arms. Those bright pink knots visible in telescopic images are not just decorative, they are stellar nurseries, massive regions where new stars are being born at a furious rate because of the interaction. This makes the Whirlpool a starburst galaxy, a system where star birth has been dramatically enhanced by a cosmic encounter. Far from destroying the spiral, the gravitational dance has amplified and defined it, proving that chaos can give birth to breathtaking structure. The Whirlpool Galaxy serves as a living laboratory, showing astronomers how these interactions not only build galaxies but can also shape their most iconic features, turning a quiet spiral into a brilliant star-forming pinwheel. But what happens when the dance finally ends? When two spirals, like those we have seen, complete their merger, they do not form a bigger spiral. They create something entirely different, a cosmic phoenix born from the ashes of chaos. The final product of a major galactic merger is often a giant elliptical galaxy. These are the behemoths of the universe, smooth, roundish, and golden-hued, lacking the delicate arms and dust lanes of their spiral progenitors. They are the end state of the gravitational waltz, where all that beautiful structure has been erased. The merger process is so violent and transformative that it completely randomizes the orbits of billions of stars. In a spiral galaxy, stars move in an orderly, disk-like rotation, like cars on a circular racetrack, but during a merger, that orderly flow is shattered. The gravitational tides act like a cosmic mixer, stirring the stellar populations until their orbits are scrambled into every possible direction, creating a three-dimensional swarm. The result is that characteristic smooth, featureless ellipsoid, a galaxy without clear internal structure but brimming with ancient stars. A perfect example of this legacy lies 55 million light-years away in the heart of the Virgo cluster. Messier 87, or M87, is a supergiant elliptical galaxy. It is a monster containing perhaps 1 trillion stars, and it dominates its region of space. Its smooth, diffuse glow is the textbook result of a violent merger history, but M87 holds another, more famous clue to its turbulent past. At its very center lies an unfathomably dense object, a supermassive black hole with the mass of 6.5 billion suns. This is not a coincidence. Astronomers believe that when galaxies merge, their central black holes are dragged together by gravity and gas, eventually spiraling inward and combining. This process feeds the resulting black hole and can unleash titanic jets of energy, like the famous jet streaming from M87's core that was recently imaged by the Event Horizon telescope. The immense size of M87 and the power of its central engine are both likely legacies of a past filled with galactic collisions. It stands as a silent, golden monument to the fact that the universe's largest structures are built not in isolation, but through a long, slow, and ultimately unifying dance. This furious birth of new suns is one of the most spectacular consequences of the galactic dance. When two galaxies intertwine, their greatest resource, vast clouds of interstellar gas and dust, become the fuel for a cosmic fireworks display. Astronomers call this a starburst, a period where star formation ignites at a rate hundreds, even thousands of times faster than in a quiet galaxy like our own. It is the universe's most prolific nursery, and gravity is the midwife. The mechanism is both simple and powerful. As the galaxies interact, their immense clouds of hydrogen gas do not pass smoothly through one another, they collide and compress. Think of it like two hands clapping together with the gas clouds caught between them. This sudden, violent compression creates regions of incredible density where gravity can no longer be resisted. Knots within the clouds collapse under their own weight, heating up until nuclear fusion sparks in their cores and a new star is born. Not just one star, but millions, all in a relatively short cosmic timespan. The result transforms the appearance of the merging galaxies. They blaze with the intense blue-white light of massive, hot, young stars, and their spiral arms or tidal tails become dotted with brilliant pink nebulae, the glowing cradles of stellar birth. An iconic example of this stellar frenzy is the Antennae Galaxies, a pair of spirals caught in an advanced state of collision. Here, the two galaxies have already passed through each other, and their long tidal tails, resembling an insect's antennae, stretch far into space. But the real action is in the chaotic overlap of their cores. This region is a maelstrom of creation, shining with the light of thousands of giant star clusters, each containing up to 1 million newborn stars. The entire system is a riot of star formation, so intense that it will likely exhaust its gas reserves in just a few 100 million years, a blink of an eye on the galactic clock. Yet such brilliance comes at a cost. Starbursts are not gentle events. The most massive stars born in these bursts live fast and die young, exploding as supernova within only a few million years. These titanic explosions seed the surrounding gas with heavy elements, but they also blast material away, helping to eventually quench the very star-forming frenzy they came from. A starburst galaxy is thus both a scene of magnificent creation and violent end, a temporary, brilliant flash in the slow, dark dance of the cosmos. Those brilliant, chaotic starbursts are often framed by the most elegant structures in the cosmic dance, long luminous streamers that arc gracefully through the darkness. These are tidal tails, the ribbons of the dance, and they are far more than just beautiful accidents. When two galaxies draw near, the difference in gravitational pull between their near and far sides stretches them, pulling out vast filaments of stars, gas, and dust. These structures can span hundreds of thousands of light years, becoming the most visible and lasting signature of an encounter. It is crucial to understand that these are not trails of debris left behind from a crash like the wake of a ship. They are material pulled from the very bodies of the galaxies themselves, flung out into intergalactic space by immense tidal forces. This makes them cosmic forensic evidence. By studying the length, curvature, and composition of a tidal tail, astronomers can work backwards like detectives reconstructing a crime scene. They can estimate the masses of the galaxies involved, the angle of their approach, and even how long ago their gravitational tango began. A perfect example is already in view: the Antennae Galaxies. Their name comes directly from their two most spectacular features, those long, antenna-like tails that give the pair its distinctive shape. These tails were created during the galaxy's first close pass, when gravity reached in and pulled their spiral arms into these immense streamers. Now, as the galactic cores fall back together for their final merger, the tails remain as a permanent record of that initial encounter. To decode this record, scientists turn to sophisticated computer simulations. They input different starting conditions, masses, and angles of approach, and let the virtual galaxies interact under the laws of physics. The goal is to produce a simulation whose tidal tails match exactly what we see in telescopes. When they find that match, they have essentially rewound the cosmic film, revealing the precise steps that led to the magnificent structure we observe today. So every graceful arc of light is a sentence in a story, written in the language of gravity, telling us how the dance began. Not every galactic dance is between equals. Sometimes a much larger partner will simply consume a smaller one. This process, known as galactic cannibalism, is a quieter, more one-sided affair, yet it is just as crucial to building the giants we see today. Our own Milky Way is not an innocent bystander in this cosmic drama. It is an active predator, growing by devouring its smaller neighbors. Right now, a dwarf galaxy known as the Sagittarius dwarf spheroidal is in its death throes, being slowly torn apart by our galaxy's immense gravity. Over billions of years, our galaxy's gravitational tides have stretched this small satellite into a long, looping stream of stars that wraps around the Milky Way like a celestial ribbon. We are witnessing a meal in progress. This is not a violent, head-on collision like the Antennae Galaxies, but a gradual dissolution. The dwarf galaxy's stars are being stripped away one by one, joining the vast halo of our galaxy and leaving behind a shimmering trail of galactic debris. Astronomers call these structures stellar streams, and they are the fossilized evidence of past mergers. They are like breadcrumbs left across the sky, telling the story of what our galaxy has consumed. By mapping the positions, motions, and even the chemical compositions of the stars in these streams, scientists can perform a kind of galactic archaeology. They can rewind time, tracing the stream back to its source to determine when the merger began. what the original dwarf galaxy was like and how its stars are now enriching the Milky Way. This process of accretion, of adding smaller systems to a larger one, is how galaxies like ours have grown to their present size. Every giant elliptical galaxy and every majestic spiral like the Milky Way stands atop a mountain of consumed dwarfs. So when you look up at the band of the Milky Way, remember you are not just looking at our home, you are looking at a cosmic graveyard and a monument to a history of quiet, relentless consumption. Yet for all the visible chaos of colliding stars and glowing gas, the true conductor of this cosmic ballet remains unseen. The most massive partner in every galactic dance is not made of stars or gas at all. It is dark matter. This mysterious substance, which neither emits nor reflects light, is the invisible scaffolding of the universe. Every galaxy, including our own Milky Way, is embedded within a vast, diffuse halo of this enigmatic material. In fact, the luminous stars and glowing nebulae we see in telescope images represent only a tiny fraction of a galaxy's total mass. The overwhelming bulk, perhaps 85%, is this invisible dark matter halo. It is this halo that provides the primary gravitational anchor, the deep well of gravity that dictates how a galaxy moves and interacts with others. When two galaxies begin their dance, it is not their visible stars that make first contact. Long before the spiral arms even begin to warp, their immense dark matter halos start to overlap and intertwine. This unseen framework sets the stage, establishing the gravitational landscape that the visible matter must then follow. The stars and gas are like leaves floating on the surface of a deep, invisible pond, their motion dictated by the powerful, unseen currents flowing beneath. This means the beautiful tidal tails, the starbursts, and the final merger are all secondary effects, playing out within a pre-established arena of dark gravity. The visible light show is merely the finale, the luminous echo of a drama that began in the dark. But how can we be so sure this invisible conductor even exists? One of the most compelling pieces of evidence comes from a cosmic collision so violent it has been named the Bullet Cluster. This is not a merger of two galaxies, but of two entire galaxy clusters, each containing hundreds of galaxies. They have slammed into one another at unimaginable speed. During this collision, something extraordinary happened. The different components of the clusters behaved in separate ways. The hot gas between the galaxies, which makes up most of the ordinary visible mass, was slowed and heated by the impact, creating a shock wave. It now sits in the center of the collision, glowing in X-rays. But the galaxies themselves, and more importantly, the bulk of the mass, kept right on going. Astronomers mapped this mass not by looking for light, but by observing how the cluster's gravity warps the light from more distant galaxies behind it, a phenomenon called gravitational lensing. This map revealed that the majority of the mass had sailed right through the collision, now residing in two distinct regions far away from the stalled gas. This is a direct observational proof. The ordinary matter, the gas, interacted and got stuck. The dark matter, which does not interact with anything except through gravity, passed through unscathed, carrying most of the mass with it. The Bullet Cluster shows us in a single, stunning image that the luminous universe we see is just the tip of a much larger, darker iceberg. It confirms that dark matter is not a theoretical idea, but a physical reality that shapes the cosmos. It is the true choreographer, the silent music, and the massive stage upon which the Dancing Galaxies perform their luminous billion-year waltz. The Antennae Galaxies are a cosmic train wreck in progress. These two spiral systems, catalogued as NGC 4038 and NGC 4039, have moved far beyond the graceful tidal stretching of the mice galaxies and are now deep in a violent, messy collision. Their cores are a swirling chaos of stars, gas, and dust, violently churning together as gravity works to blend them into a single new entity. This is not a future prediction. It is a reality unfolding 50 million light-years away, and it offers us a front-row seat to the most intense phase of the galactic dance. Within this maelstrom, the most spectacular feature is the furious birth of new stars. Vast clouds of colliding gas have been compressed to their breaking point, igniting a hyper-starburst. Dozens of superstar clusters have formed, each one a dazzling knot containing up to 1 million newborn suns. These clusters are the powerhouses of the merger, blazing with the intense blue light of massive, hot stars that live fast and die young. To understand the full fury of this collision, we must look beyond visible light. The Hubble Space Telescope's iconic images show the beautiful, tortured structures and the glowing pink nebulae of stellar nurseries. But when the Chandra X-ray Observatory peers at the same scene, it reveals a far more violent landscape. Its X-ray vision detects the searing glow of countless supernova remnants, the expanding shells of gas from exploded stars, and brilliant points of light that are X-ray binaries. These are pairs where a normal star orbits a neutron star or black hole, with material being ripped from the star and heated to millions of degrees as it spirals in. This X-ray cacophony is the direct result of the starburst, a signature of the short, explosive lives of the most massive stars born in the frenzy. The antennae are more than a distant spectacle, they are a prophetic mirror. The dance we witness here is precisely what awaits our own galaxy in the distant future. In about 4.5 billion years, the Milky Way and the Andromeda Galaxy will begin a similar slow-motion collision. While it is unlikely stars will physically crash, the gravitational chaos will warp our familiar spiral, trigger our own era of rampant star birth, and ultimately blend our two galaxies into a new elliptical giant. So when you see an image of the antennae, you are not just looking at a beautiful catastrophe, you are witnessing the fate of our own cosmic home, a preview of the final, unifying act in a dance that began at the dawn of time. This violent, beautiful fate is not just for distant galaxies, it is the destiny written for our own home. The Milky Way is currently on a collision course with our largest neighbor, the Andromeda Galaxy. Right now, Andromeda is a faint, fuzzy patch in the constellation that bears its name, a quiet smudge of light 2.5 million light-years away. But that distance is closing. Every second, our two galaxies rush toward each other at a staggering speed of about 110 kilometers per second, drawn together by the mutual pull of their immense dark matter halos. The countdown has been running for billions of years, and the clock is ticking down to an inevitable, spectacular meeting. The timeline for this cosmic event stretches across epochs almost impossible to comprehend. In roughly 4.5 billion years, the Milky Way and Andromeda will begin their first close gravitational pass. They will not smash directly into one another like two cars in a cosmic freeway pile-up. Instead, they will begin a long, intricate dance, a series of ever-tightening orbits that will last for another 2 to 3 billion years. For a future observer, if any could exist on a world that far ahead, the night sky would transform slowly from a familiar band of stars into a scene of breathtaking chaos and creation. During the first close approach, gravity will begin its sculpting work. The orderly spiral arms of our galaxy will warp and distort, pulled out of shape by Andromeda's immense gravitational tides. The entire structure of the Milky Way, as seen from within, would become unrecognizable. The serene band of light we know would twist and contort. Andromeda itself, now filling a huge portion of the sky, would also be stretched, its spiral shape mangled by the encounter. Long, luminous tidal tails of stars, gas, and dust would be pulled from both galaxies, streaming out into the intergalactic void, creating celestial bridges of stolen material. Then the starburst would ignite. Just as we see in the Antennae Galaxies, the collision of vast interstellar gas clouds will trigger a frenzy of new star formation. The sky would blaze with the light of millions of newborn stars and the glowing pink nebulae that cradle them. It would be a period of both terrifying disruption and magnificent cosmic fertility. After this initial pass, the galaxies will swing apart, only to be pulled back together by gravity's unrelenting grip. They will perform another loop, and then another, each orbit drawing them closer, their structures becoming more and more intertwined. Finally, after billions of years of this gravitational waltz, they will merge completely. The two distinct spirals will cease to exist. The orderly rotation of their stellar disks will be randomized by the chaotic gravitational forces, blending the billions of stars from both galaxies into a new, smooth, and nearly featureless shape. The product of this ultimate union will likely be a giant elliptical galaxy. Astronomers have playfully given this future entity names like Milkomda or Milkdromda. Our Sun, if it still exists, will be flung into a new, wild orbit within this vast stellar swarm. The night sky from Earth, or whatever remains of it, will be utterly alien. The familiar Milky Way will be gone, replaced by a diffuse, golden glow of ancient stars with no spiral arms, no dark dust lanes, and no nearby galactic neighbors in sight. The dance that built the cosmos will have taken our home and remade it into something entirely new, a silent monument to the universe's endless cycle of creation through collision. But how can we possibly know the steps of a dance that takes longer than Earth has existed? Astronomers have a remarkable tool for this, a cosmic time machine built not from metal and glass but from lines of computer code. To unravel the history of colliding galaxies, they turn to the power of supercomputer simulations. These are not simple animations or artistic guesses. They are rigorous digital universes governed by the same laws of physics that shape our own. The process begins with a set of starting conditions. Scientists define the initial properties of two virtual galaxies, their masses, their speeds, their shapes, and the angle at which they approach one another. They then program in the fundamental forces, primarily gravity, and set the simulation in motion. The supercomputer calculates the gravitational pull between every single particle in the system, step by tiny step, across what would be billions of years. It is a staggering amount of calculation, but the result is a movie of a galactic merger unfolding before our eyes. The true test, however, is in the comparison. Astronomers run their simulation and then look at the final product. Does it create the same long, graceful tidal tails seen in the mice galaxies? Does the merger produce a starburst and eventually a smooth elliptical galaxy that matches real ones like Messier 87? If the simulation's output aligns perfectly with telescopic observations, then the scientists know their initial assumptions about the galaxy's masses and trajectories were likely correct. They have effectively rewound the cosmic film. This process allows them to decode the past from a single, static image we see in the present. The most advanced simulations today go far beyond simple gravity. Projects like the Illustris TNG simulation are monumental endeavors that model not just the dance of dark matter and stars, but the complex behavior of interstellar gas. They include the physics of how gas cools, collapses to form stars, and how those stars then explode, enriching the gas with heavy elements. They even simulate the powerful feedback from supermassive black holes, whose energetic jets can heat gas and shut down star formation. By incorporating all these interconnected processes, these simulations can grow entire model universes from near the Big Bang to the present day, producing populations of galaxies that look and behave astonishingly like the real ones we observe. When we watch a visualization from such a simulation, we are not seeing an artist's impression. We are witnessing a prediction of physics, a digital echo of the real cosmic ballet that has been playing out for over 13 billion years. These simulations show us the grand, predictable patterns of the dance. Yet the universe always has a surprise waiting in the wings. Some of the most profound mysteries in modern astronomy come not from the brilliant collisions, but from the galaxies that seem to have missed the music entirely. They are called ultra-diffuse galaxies, and they defy almost everything we thought we knew. Imagine finding a ghostly cosmic jellyfish, a galaxy as wide as our entire Milky Way, spanning tens of thousands of light years, but one that holds only a pathetic 1% of the stars. That is an ultra-diffuse galaxy. They are so faint, so ethereal, that they blur the line between a galaxy and a wisp of intergalactic haze. For decades, they slip through our telescopes unnoticed, mere smudges dismissed as camera defects or distant background noise. Only with the most sensitive modern instruments have we begun to pull these phantoms into focus, and what we see is deeply confusing. Take Dragonfly 44, discovered in the Coma Cluster. It has the stellar mass of a tiny dwarf galaxy, but its stars are spread out over a volume as vast as the Milky Way. The result is an object of incredible dimness, a gauzy veil of ancient stars. The immediate question is, what holds it together? With so few stars, there is not nearly enough visible gravity to prevent it from simply flying apart. The answer initially seemed to be the same as for all galaxies, an immense halo of dark matter. Measurements suggested Dragonfly 44 was in fact almost entirely dark matter, a ghostly frame with barely any luminous decoration. This made it a fascinating extreme, a galaxy that was all invisible skeleton with almost no flesh. But then came an even bigger puzzle, NGC 1052 DF2. This ultra-diffuse galaxy presented the opposite problem. Studies of the motions of its star clusters and globular clusters revealed something astonishing. There was no detectable dark matter holding it together at all. The visible stars accounted for all the gravity in the system. This was and remains a monumental challenge to our models. How do you form a large, coherent galaxy without the gravitational anchor of dark matter? It should have been ripped apart long ago. These bizarre objects force astronomers to consider radical ideas. One leading theory is that they are the casualties of the cosmic dance, the failed galaxies. Perhaps they were normal dwarfs long ago, but during an early encounter with a giant neighbor in their cluster, all their life-giving gas was violently stripped away. Robbed of the fuel to make new stars, they were left as bloated, aging relics, their remaining stars drifting slowly apart. Another idea suggests they are just ancient dwarfs that formed in a peculiar, quiescent way, their stars born in a brief, initial burst and then left to drift for eons without further activity. Or perhaps NGC 1052 DF2 is the result of a different kind of interaction, a high-speed encounter that somehow ripped away not just its gas, but its dark matter as well, leaving behind a pure cloud of stars. Every ultra-diffuse galaxy is a question mark. They challenge the fundamental relationship we thought existed between dark matter and visible matter, the partnership that builds every other galaxy we see. Are they the sad remnants of dances that went terribly wrong, or are they something else entirely, a forgotten chapter in the story of how structure forms in the cosmos? Their very existence tells us that for all we have learned about the grand ballet of colliding giants, we are still just beginning to understand all the quiet, strange, and lonely steps that are possible in the dark. At the heart of this galactic chaos lies an even more incredible phenomenon. Every large galaxy we have discussed, from the graceful Whirlpool to the colossal Messier 87, harbors a secret at its core, a supermassive black hole. These are not the stellar mass black holes formed from dying stars, but incomprehensibly dense monsters with masses millions or even billions of times that of our Sun. They sit in the central darkness, governing the motion of stars around them. When two galaxies begin their slow dance, these titanic engines are destined for a duet of their own. As the galaxies merge and their stars are scrambled into a new elliptical shape, a fascinating gravitational process begins. The two supermassive black holes, each once the ruler of its own domain, are dragged along with the flow of stars toward the new galaxy's center. They sink through the dense stellar environment through a process called dynamical friction, where their immense gravity slingshots surrounding stars, losing energy and spiraling ever inward. Eventually, they find each other, Locked in a mutual gravitational embrace, they form a binary pair, two unfathomable weights orbiting a common point. This is the final, deepest layer of the cosmic dance. As they circle, they do so in near-perfect silence, for black holes emit no light, but they do not spin quietly. Their orbital motion creates ripples in the very fabric of spacetime itself, gravitational waves. These are not waves of light or sound, but literal distortions in the geometry of the universe, predicted by Einstein over a century ago. As the black holes lose energy by emitting these waves, their orbit shrinks. They spiral closer and closer over millions of years, their dance accelerating until, in a final, unimaginable flash of gravitational radiation, they collide and merge into a single, even more massive black hole. We may have already found a pair performing this penultimate act. In a galaxy over 3.5 billion light-years away, astronomers study a brilliant beacon called OJ-287. This is a blazar, a galaxy whose central black hole is actively feeding, shooting a jet of radiation almost directly at Earth. But its light does not shine steadily. It erupts in violent bursts roughly every 12 years. The leading explanation is that OJ-287's supermassive black hole is not alone. It has a partner, a second, smaller but still colossal black hole orbiting it. As this smaller black hole plunges through the disk of gas swirling around its larger companion, it triggers titanic explosions of light we see as flares. If this model is correct, we are witnessing a binary supermassive black hole system in its final millennia before merger. To truly hear this cosmic finale, however, we need a new kind of ear. Our current ground-based observatories can detect gravitational waves from the mergers of stellar mass black holes, but the deeper, lower frequency waves from these supermassive behemoths are beyond their reach. That is the promise of a future mission called LISA, the Laser Interferometer Space Antenna. Planned as a trio of satellites flying in a giant triangle millions of kilometers apart, LISA will sense the subtle stretching of space caused by passing gravitational waves. It will listen to the low-frequency hum of the universe, the chorus of countless supermassive black hole binaries spiraling together across cosmic time. With LISA, we will not just see the aftermath of the dance in distorted galaxies. We will hear the final, thunderous notes of the black hole duet itself, a direct soundtrack to the universe's most powerful collisions. The ring of the Cartwheel Galaxy is a perfect cosmic bullseye, a target painted across 75,000 light-years of space. It stands as one of the most visually striking and peculiar results of a galactic collision, a rare ring galaxy whose form tells a story of a direct and devastating hit. Unlike the messy mergers we have seen, the Cartwheel's structure is precise and geometric. It features a bright, dense inner ring of young stars surrounding the galactic core, and a spectacular, colorful outer ring that blazes with the blue light of intense star formation, connected by faint, spoke-like structures of dust. This is not the product of a glancing blow or a slow merger, but of a cosmic bullet shot straight through the heart. The leading theory is as dramatic as the image itself. Several 100 million years ago, a smaller companion galaxy, one of the two visible nearby, did not swing past the cartwheel. It plunged directly through its center. Imagine throwing a stone into a still pond. The impact sends a circular wave rippling outward from the point of contact. In this cosmic analogy, the intruding galaxy was the stone, and the larger spiral's disk of gas was the pond. The gravitational shockwave from the direct collision compressed the gas as it raced outward. This compression wave, traveling at hypersonic speeds, triggered a chain reaction. Where the wave passed, vast clouds of gas were squeezed past their breaking point, collapsing under gravity to ignite a firestorm of new stars. This is why we see that brilliant outer ring. It is the leading edge of that shockwave, a propagating circle of stellar birth frozen in time. The smaller galaxy, having blasted through, continued on its way, forever altered but still visible as one of the companions in the system. The Cartwheel Galaxy is a masterpiece of celestial cause and effect. It demonstrates with perfect clarity that the geometry of a collision is everything. A different angle, a slower speed, and we would see a pair like the mice or the antennae. But a direct, piercing impact creates this rare and beautiful bullseye, a temporary phase in the galaxy's life that will eventually settle, leaving behind a completely reshaped and unique galactic form. The most dramatic galactic dances did not happen in the modern universe, but in its chaotic, formative youth. To understand why, you must shrink the cosmos. Rewind time over 13 billion years, and you find a universe that is far denser and more intimate. Space itself was more compact, and galaxies were packed closer together like dancers in a crowded ballroom. In this environment, collisions and mergers were not rare, spectacular events. They were the primary method of construction. The first galaxies were small, fragile things, often just clumps of stars and gas. To grow into the majestic spirals and giants we see today, they had to merge. This was the era of the galaxy builders, a time of constant, violent assembly where the cosmic dance was not a slow waltz but a frantic, energetic scramble. We now have a front row seat to this ancient construction zone, thanks to the James Webb Space Telescope. Its infrared eyes peer back further than any instrument before, capturing light from the universe's first billion years. What it shows is not the neat, defined spirals of today, but a menagerie of oddities. We see galaxies that look like glowing train wrecks, smears of light, and chains of brilliant knots. These are not finished products, they are galaxies caught in the act of merging, their shapes stretched and distorted by violent gravitational encounters. They are clumpy, irregular, and blazing with the light of newborn stars, a direct snapshot of the building process in action. These ancient mergers did more than just pile stars together, they ignited the most powerful engines in the cosmos. At the heart of many of these young, merging galaxies, a monster was awakening. The collision funnels vast amounts of gas directly toward the center, feeding the nascent supermassive black hole lurking there. As this gas spirals in at incredible speeds, it heats up to millions of degrees, blazing with a light that can outshine the entire galaxy. This is a quasar, a beacon of terrifying energy. In the early universe, quasars were far more common, and their ignition was almost always tied to the violent fuel delivery of a galactic merger. These brilliant beacons, powered by the dance of galaxies, became the lighthouses of the young cosmos. But their legacy is even more profound. The furious activity around these ancient black holes and the supernova explosions from the merger-induced starbursts performed a crucial alchemy. They forged heavy elements like carbon, oxygen, and iron, and then blasted them out into the surrounding space. This cosmic pollution was a gift. It seeded the primordial gas clouds with the raw materials for rocky planets, organic molecules, and eventually life. Every iron atom in your blood, every calcium atom in your bones, was forged in the heart of a star or the disk around a black hole, and then scattered across the universe by these violent, ancient dances. The chaotic mergers of the early universe were not just builders of structure, they were the furnaces that enriched the cosmos, setting the chemical stage for everything that was to come, including us. Floating in the void between two galaxies, a ghost haunts the constellation Leo. This is not a galaxy, nor a nebula in the familiar sense. It is the Leo ring, a colossal, faint loop of primordial hydrogen, gas so vast it could comfortably contain our entire Milky Way. Drifting in the Leo group of galaxies, this ethereal structure orbits not one, but two large galaxies, M105 and NGC 3384, like a cosmic smoke ring left behind by a forgotten giant. Its existence is a profound puzzle, a whisper from a collision that occurred over 1 billion years ago. Most tidal tales, like those of the Antennae Galaxies, are rich with the brilliant pink glow of stellar nurseries, their compressed gas bursting into new suns. But the Leo ring is dark. It holds enough raw material to build hundreds of millions of stars, yet it contains almost none. It is a reservoir of potential that has stubbornly refused to ignite, a fossil of pure, unused fuel. This makes it a celestial anomaly that challenges our very understanding of how gas behaves during the galactic dance. The prevailing theory is that the ring is the leftover tidal tail from a direct yet strangely gentle collision between two large galaxies in the distant past. The gravitational interaction pulled out this immense loop of gas, but for reasons we are still deciphering, the conditions were never right for it to collapse and form stars. Perhaps the collision was a particularly clean, high-speed encounter that stretched the gas without compressing it enough. Or maybe the gas in these ancient galaxies was too hot or too diffuse to clump together effectively when pulled out into the lonely intergalactic space. Some scientists even speculate that the magnetic fields within the gas are unusually strong, providing a supportive force that counteracts gravity's pull, preventing the birth of stars. Whatever the reason, the Leo ring stands as a silent monument to a different kind of dance. It proves that not every galactic encounter ends in a fireworks display of starbirth. Some leave behind only echoes, vast and quiet structures that hold their secrets for eons, reminding us that for every rule the cosmos establishes, it creates a beautiful, mysterious exception. Hoag's object is a cosmic enigma of almost impossible perfection. Floating 600 million light-years away in the constellation Serpens, it looks less like a galaxy and more like a celestial jewel, a hypnotic ring of sapphire blue stars encircling a golden, spherical core. The ring itself is a perfect circle of intense star formation, young and brilliant, while the central hub glows with the older, yellower light of ancient suns. Between them lies a dark, seemingly empty gap, a deep moat of space that cleanly separates the two distinct populations of stars. This breathtaking symmetry presents astronomers with a beautiful and stubborn puzzle. How does a galaxy become so perfectly divided? The most intuitive answer points to the violent dances we have already witnessed. Could Hoag's object be a more evolved, more serene version of the Cartwheel Galaxy? In that scenario, a smaller galaxy pierced the center of a larger spiral billions of years ago. The gravitational shockwave would have triggered a ring of star formation that propagated outward, while the intruder itself was either absorbed or flung away, leaving the old core intact. Over eons, the ring would have expanded and smoothed into this near-perfect circle, its initial chaos giving way to serene order. This merger theory is compelling, but there is a significant complication, a complete lack of evidence. Searches for a second galaxy, a potential bullet that caused the impact, have come up empty. There is no obvious culprit, no nearby companion showing the scars of such an encounter. This absence forces scientists to consider a radically different origin story, one that requires no collision at all. Perhaps Hoag's object is the product of an extreme internal instability, a phenomenon known as a resonance. In this model, it began as a fairly ordinary rotating disk galaxy. Over time, gravitational waves or a lopsided distribution of mass within the disk could have created a standing wave, a stable ripple that swept through the gas. This ripple would have gathered material into a dense, expanding ring, compressing gas to ignite new stars while the central region was left behind, starved of fuel and aging in isolation. This process could, in theory, create a ring without any external trigger, a galaxy reshaping itself from the inside out. Yet even this elegant explanation struggles with the object's pristine symmetry. Internal instabilities tend to create more messy, asymmetric structures, not this flawless cosmic bullseye. The sheer beauty of Hoag's object is what makes it so scientifically vexing. It stands alone, a singular masterpiece that defies our neat categories. Is it the ghost of a forgotten collision, its evidence now faded into the darkness? Or is it a rare and stable configuration that a galaxy can achieve all on its own, a natural form we simply have not seen elsewhere. For now, it remains one of the universe's most captivating mysteries, a reminder that for every rule we decipher in the chaotic dance of galaxies, there exists a serene and perfect exception, quietly challenging everything we think we know. So does the galactic dance lead to a cosmic death? When we witness two spirals like the Antennae Galaxies merge into a smooth, golden elliptical, it is easy to see it as an ending. The distinct, vibrant identities of the original galaxies are erased, their beautiful structures randomized into a featureless swarm of stars. In that very specific sense, yes, those individual galaxies do die. They cease to exist as the unique cosmic islands they once were. But this is not a story of destruction, it is a story of profound transformation. Think of it not as a funeral, but as a grand unification. Every single star, every planet, every speck of dust from both galaxies survives the merger. They are not annihilated, they are simply blended into a new, larger whole, like two distinct colors of paint mixed on a palette to create a third, richer hue. The supermassive black holes at their cores spiral together, creating a single, more massive gravitational anchor. The dance does not erase the participants, it reorganizes them into a new cosmic entity with a combined history and a unified future. This transformative process is the primary way galaxies grow and evolve across cosmic time. Our own Milky Way is a living library of such mergers, its halo filled with the stellar streams of dwarfs it consumed long ago. So while the spiral parent galaxies may be gone, their legacy lives on in every star of the new elliptical giant. However, there is another, quieter fate that can stem from the dance, one that truly does end a galaxy's vibrant life. Remember the furious starbursts triggered by collisions, those brilliant bursts of newborn stars. That frenzy has a hidden cost. The most massive stars born in these bursts live for only a few million years before exploding as supernova. When they do not just shine brightly, they act like cosmic bombs. These sequential, powerful explosions can generate immense galactic winds, blasting the remaining star-forming gas out of the galaxy entirely, hurling it into the vast intergalactic void. Once this fuel is lost, the galaxy's engine sputters and stops. No new gas means no new stars. The brilliant blue light of short-lived, massive stars fades away, leaving behind only the longer-lived, older and redder stars. The galaxy gradually changes color from blue to yellow to red. Its stellar population ages in unison with no fresh young stars to renew it. This is how a galaxy becomes what astronomers call red and dead. It is still full of stars, but they are all ancient, and the galaxy itself is a quiet, fading ember. Many of the giant elliptical galaxies we see, like Messier 87, are in this state. They are the products of past mergers, their gas exhausted by the very starbursts that made them brilliant, now left as smooth, red, and quiescent monuments to a more violent and fertile youth. So the dance offers two profound outcomes, a transformative rebirth into a larger structure, or a gradual fading into a red and dead retirement. In both cases, nothing is truly lost, only changed, reminding us that in the cosmos, even an ending is just another step in an endless cycle of rearrangement. The final, unifying collision of supermassive black holes does not end in silence. It creates a new kind of music, one written on the fabric of space itself. These are gravitational waves, the ripples in spacetime predicted by Einstein, and they carry a frequency so low they are more a deep, resonant hum than a sharp chirp. When two galaxies merge, their central black holes eventually spiral together, and this final act of union releases a tremendous burst of gravitational energy, shaking the very structure of the universe. But this is not a solo performance. Across the cosmos, countless supermassive black hole binaries are in various stages of this slow, inward spiral. Together, they create a constant, overlapping chorus of these low-frequency waves, a gravitational wave background that permeates all of space. This is the true music of the spheres, a cosmic hum echoing the merger history of the universe from its earliest epochs to the present day. To hear this hum, we cannot use telescopes that collect light. We need an instrument of exquisite patience and precision, a galactic scale detector. Enter the pulsar timing array. This ingenious approach uses nature's most perfect clocks, millisecond pulsars. These are the rapidly spinning cores of dead stars, beaming out pulses of radio waves with a stability that rivals our best atomic clocks on Earth. Projects like the North American Nanohertz Observatory for Gravitational Waves, or NanoGrav, monitor an entire array of these pulsars across our galaxy, meticulously tracking the arrival time of their pulses over years and decades. The theory is elegant. As a gravitational wave, that low hum from distant black hole mergers passes between Earth and one of these pulsars, it will minutely stretch and compress the space in between. This will cause the pulsar's clock-like ticks to arrive at our telescopes ever so slightly early or late. No single pulsar's drift would be convincing, but by looking for a correlated pattern of timing shifts across dozens of these celestial metronomes spread across the sky, scientists can separate the signal from the noise. They are listening for a specific, symphony-like pattern in the data, the signature of the gravitational wave background. A confirmed detection would open an entirely new sense with which to perceive the cosmos. It would be a direct soundtrack to the slow-motion dance of galaxies and their monstrous black hole hearts, a history written not in light but in the subtle vibrations of space-time. We would no longer just see the aftermath of the dance in beautiful Hubble images. We could listen to its ongoing, universe-filling rhythm. Not every galactic encounter leads to a beautiful merger or a brilliant ring. In the most crowded neighborhoods of the universe, the dance floor itself can be a dangerous place. Within the dense cores of galaxy clusters, home to hundreds or thousands of galaxies, a different kind of interaction dominates. Here, the slow, intimate waltz is replaced by something more akin to a chaotic, high-speed crowd. Galaxies whip past one another at thousands of kilometers per second, their gravitational fields brushing and tugging as they go. This relentless series of close encounters has a name: galaxy harassment. It is not a single catastrophic event, but a death by 1,000 gravitational cuts. Each high-speed pass delivers a slight gravitational jerk, a subtle pull that over millions of years can completely reshape a victim. A beautiful, orderly spiral galaxy with its flat disk and winding arms is particularly vulnerable. These repeated gravitational slaps can heat up the orbits of its stars, randomizing their motions and puffing out the delicate disk into a bloated, shapeless elliptical. The galaxy is not consumed, but it is utterly morphed, its identity erased by the constant buzz of the crowd. There is another, even more direct threat in these crowded clusters, one that attacks a galaxy's very lifeblood. Between the galaxies in a cluster is not empty space, but a searing soup of superheated gas known as the intracluster medium. This gas is thin, but it is incredibly hot, often reaching tens of millions of degrees. When a spiral galaxy, rich with its own cooler clouds of star-forming gas, plunges through this environment, it experiences a cosmic version of a hurricane-force wind. Astronomers call this ram pressure stripping. Imagine holding a handful of fine dust and running at full speed into a powerful gale. The lighter dust, your galaxy's cold gas, is ripped right out of your grip, while the heavier pebbles, the stars, remain in your hand. That is precisely what happens. The pressure from the intracluster medium acts like a violent wind, physically stripping the cold gas from the galaxy as it moves. This gas is the raw material for new stars. Once it is gone, star formation grinds to a halt. The galaxy is left with its aging stellar population, destined to redden and fade, a process known as quenching. The evidence of this violent stripping is both beautiful and tragic. In several galaxy clusters, astronomers have found what they call jellyfish galaxies. These are spirals with long, trailing tentacles of gas that stream behind them, exactly like a jellyfish drifting in a current. These luminous tails are not made of stars, but of the galaxy's own interstellar gas, being forcibly torn away by the ram pressure as the galaxy speeds through the cluster. The galaxy at the head of this stream is often already showing signs of distress, its star formation being strangled as its fuel supply is stolen. These jellyfish galaxies are cosmic snapshots of a galaxy in the process of being robbed of its future. They show us that the dance floor of a dense cluster is a harsh and unforgiving environment where the music is too fast, the crowd is too thick, and simply moving through the room can strip a galaxy of its potential, leaving it to slowly fade in the brilliant, crowded darkness. Finding these galactic dancers requires seeing the universe in more than just visible light. To truly understand the mechanics of a merger, astronomers must listen to the full symphony of the electromagnetic spectrum, with each wavelength revealing a different instrument in the cosmic orchestra. The iconic images from the Hubble Space Telescope give us the breathtaking visible light portrait, showing the warped structures, tidal tails, and brilliant blue star clusters. But Hubble's view is just the surface. To peer through the thick clouds of dust that shroud the most active stellar nurseries, we need infrared eyes. Telescopes like the retired Spitzer and its revolutionary successor, the James Webb Space Telescope, see the heat glow from that dust, revealing the hidden fury of star formation within colliding galaxies that optical light cannot penetrate. Meanwhile, in the cold, quiet domain of radio waves, observatories like the Atacama Large Millimeter Array, or ALMA, map the distribution of the frigid molecular gas, the raw fuel for stars. By tuning into specific molecules, ALMA shows us where the gas is being compressed and funneled by the collision, predicting where the next starburst will ignite. And to witness the most violent energies, we turn to X-ray telescopes like Chandra. Its vision cuts through the chaos to pinpoint the searing hot gas heated by supernova shockwaves, and most importantly, to find the brilliant, accreting supermassive black holes, often revealing dual monsters in the hearts of merging systems. Each telescope is a different sense, and only by combining their views do we get the complete story of the dance. Yet the most surprising discoveries sometimes come not from billion-dollar machines, but from the collective curiosity of everyday people. In 2007, a project called Galaxy Zoo launched online with a simple goal: to harness human pattern recognition to classify the shapes of 1 million galaxies from the Sloan Digital Sky Survey. The response was staggering. Hundreds of thousands of volunteers, from schoolchildren to retirees, began clicking through galaxy images, distinguishing spirals from ellipticals and noting oddities. This massive citizen science effort did more than just catalog. It led to genuine, peer-reviewed discoveries. Volunteers identified a whole new class of small, bright, and intensely green objects, which they nicknamed Green P galaxies. These turned out to be compact powerhouses of star formation, possible analogues to the infant galaxies of the early universe. Even more remarkably, sharp-eyed participants began flagging strange, disturbed systems that algorithms had missed, systems with faint bridges and odd asymmetries. Their tags led professional astronomers to investigate, confirming they had found previously unknown galaxy mergers at various stages. The project proved that the human eye, especially thousands of them working together, possesses an unparalleled ability to spot the subtle signs of a cosmic dance. It reminds us that the universe's grandest performances can still be discovered by anyone willing to look. These discoveries, from citizen scientists to multi-million-dollar telescopes, all reveal the same fundamental truth. The universe is not a still life. It is a living, breathing entity in motion, and we are woven into its story at the most intimate level. The dance of the galaxies is not merely a distant spectacle for our telescopes. It is the very process that built our home and ultimately us. Every single atom in your body, from the calcium in your bones to the iron in your blood, carries a lineage that traces back to these cosmic collisions. Those heavy elements were not present at the birth of the universe. They were forged in the nuclear furnaces of stars, stars whose own births were often triggered by the gravitational chaos of merging galaxies. When those stars died, exploding as supernova or shedding their outer layers, they seeded the cosmos with these essential ingredients. The dance, therefore, is not just about structure, it is about chemistry. It is the universe's way of mixing, enriching, and recycling the raw materials for planets, oceans, and life itself. We are quite literally stardust that has been stirred and gathered by the gravitational waltz of galaxies over billions of years. This perspective is both grounding and awe-inspiring. It places our brief, brilliant human lives against a canvas of time so vast it defies comprehension. Our entire recorded history is less than a blink in the lifetime of a single galactic merger. Civilizations rise and fall, continents drift, and species evolve, all within a sliver of time it takes for two galaxies to complete a single graceful path. This scale invites a profound humility. Our worries, our conflicts, our triumphs all play out on a stage that is unimaginably small in both space and time. Yet, this is not a reason for despair, but for a deeper connection. We are not separate from this grand cosmic narrative, we are a product of it. The same forces that sculpt galaxies, gravity, and nuclear fusion also govern the orbits of planets and the beating of our hearts. We are embedded in this dance not as spectators, but as participants made from its ancient materials. Recognizing this changes everything. It means the universe is not a cold, empty void, but a place of dynamic, creative change. The largest structures we see, the majestic spirals and golden ellipticals, are not permanent monuments. They are temporary arrangements, waypoints in an endless cycle of coming together and drifting apart, of building up and fading away. Our own Milky Way is a transient form, destined to merge and be reshaped. This realization invites a shift in how we see our place. We are not at the center of a static universe, but we are of the universe, born from its most violent and beautiful processes. The dance of the galaxies tells us that change is the only constant, from the smallest cell to the largest cluster of stars, and in that endless transformation we find our true and deeply connected cosmic heritage. From the first gentle tidal stretch to the final, fiery embrace, this dance of attraction and chaos builds everything we see. Galaxies are not born in isolation. They are forged in the furnace of collision, their shapes, sizes, and destinies sculpted by a relentless gravitational waltz. These interactions are the universe's primary architects, constructing the grand cathedrals of stars we find scattered across the cosmos. They are the engines of creation, triggering stellar fireworks, feeding monstrous black holes, and seeding space with the very elements that make planets and life possible. What we have witnessed is a cycle as old as time itself, a fundamental rhythm of construction through destruction. Our journey through this cosmic ballet, however, is just beginning. With each new tool, we learn more steps. The future hum of gravitational wave observatories will let us hear the mergers we cannot see, while the penetrating gaze of telescopes like the James Webb peers further back, watching the first galaxies take shape through these very collisions. The dance is eternal, and we are only now learning to listen to its music. So the next clear night, find that faint smudge of light in the constellation Andromeda. Look at it not as a distant stranger, but as a future dance partner already falling toward us in a silent promise of cosmic change. What do you think the sky will look like when that dance finally begins? Share your thoughts on these grand galactic mysteries below.